spectral energy density আছে 8 pi by c cube. Total power. So first of all, spectral energy density মানে কি? Energy radiated per unit time, তাতে power হয়ে গেল in the frequency range nu and nu plus d nu. Now total power. So in whole frequency range, total power মানে কি? এটা power কেন পর radiate হয়? Like this, right? This is a small range d nu, let's say, at some nu. So at this nu and nu plus d nu, a part of just a part of kiman radiate hoy. This is this. The question was, what is the total radiated? So from here up to infinity. Okay, and that's already power because part time is there. Okay, so the power is 0 to infinity u nu d nu. That is our power. And obviously, this is going to be a function of h, t, kb, right? And nothing else. I mean, c maybe. But these are constant. The temperature, if you are interested in t, then everything else will be a constant. And the answer will be some function of t, let's say. Why not just call it pt? It will be some function of temperature. And the question was, what is that function of t? And treat everything else as a constant. So I don't really need to do the integration for that. If I just choose, so this 8 pi over c cube. So whatever that is, again a constant, just neglect that. H, let's keep that for now. So we have h, or even neglect h, doesn't matter, nu squared d nu, e to the power h nu by kbt minus 1, proportional to this, right? Now if I take, to do this integration, naturally I have to really take h nu by kbt equal to some variable. This is the first thing anyone will attempt, equal to some x. And so h by kbt d nu equal to dx. And so kbt by h here, this, right? So this will be proportional to nu. So nu is x kbt, nu is x kbt by h, right? So nu square is x square kb square t square by h square, and d nu is kbt by h dx, right? And a to the power x minus 1. I think this was cube. Yeah, because one nu square comes from the volume, and another nu comes from the actual h nu, energy, E equal to h nu, so cube. Square only in Rayleigh-Jean's law actually, so cube. So this is cube, cube, cube. So we have t cube and t, so t square, t to the 4 comes out, so all the t's are gone, and only x cube, and others are just what? Constants. So x cube dx by this. And what will be the limit? Well, if nu goes to 0, x also goes to 0. If nu goes to infinity, x also goes to infinity. So even in x variable, this is 0 to infinity. If you do this integration, it will be just a number, because x will get integrated and the final will be some function of x, and then you put the value of infinity and 0 and it will turn into a number. So which means it's again a constant. What we are left with, this power is proportional to t to the power 4. It has a name, this law. What is the name? Yeah, Stephen Boltzmann's law. Power radiated of a black body is proportional to t to the temperature to the power 4. So now we'll do the Compton scattering. This thing actually you can also derive. So in black body radiation, we first time got introduced to the fact that energy absorbed and emitted by the oscillators of the walls inside a black body are in the form of packets. These oscillators have energy as NH nu, right? Then we saw in photoelectric effect that these packets of energy are not only, restricted to the oscillators of the wall. Light itself, any electromagnetic wave itself behaves like these tiny packets. So the energy of these electromagnetic fields come as tiny particle-like something, concentrated packets. So if you reduce the, let's say, amplitude or intensity of this bulb, let's say if you reduce this like really too much, such that it's like barely visible or not even, but our retina can detect a single photon also. It's sensitive. But if you had really good eyes and if you were in complete darkness and the brightness of the bulb is so low that it's just emitting, one photon at a time, like, then it would really look like it's just ejecting some bullets. But usually there are too many of these bullets. So it looks like, a continuous fluid like something. Light or electromagnetic wave is like this. It has packets of energy and they're like bullets. So this is the first time we encountered that light can be like bullets. And we know this because this bullet hits the electrons of a metal and kicks them out. So they really are acting like bullets. And they sometimes do and sometimes they do not. One problem I gave you, the 0.5% of the time they kick out. And this is understandable. If you hit a bullet randomly, it's not necessary that you will always hit the target, right? So if it's a bullet, and if you have a bad aim, then sometimes you will miss, sometimes you will hit. So that's your 0.5%. If you know how many photons are there, and only 0.5% of them are going to hit exactly some electrons, then only 0.5% of those photons will lead to a photoelectron. Anyway, it's still something like our classical notion of a particle. This is again one more step towards that. One example. So Compton saw this in experiment, the X-ray radiation were losing a lot of energy when they are crossing through matter, let's say glass or plastic or something. When X-ray was passing through them, they were losing energy. What do we mean by losing energy? So you sent some wave, some electromagnetic wave. Let's say some X-ray, okay? X-ray is just light. Just its wavelength is about 0.1 nanometers to 10 nanometers. This range is X-ray. What is visible range? It's about 380 nanometers to some 700 nanometers. That's our all visible light. And this is our X-ray range. Smaller the wavelength means higher the frequency, means higher the energy. Okay, so he saw that an X-ray with some wavelength or some frequency, let's say he sent it through some material, and he saw that with some whatever detector, some X-rays were coming out and they had slightly lower frequency, slightly lower energy. Okay, actually roughly like 10% less than the original frequency. So what happened to that light? Where did the energy go? It got changed. Okay, and he could not explain it usually. So what he said is, this can be explained if we consider this picture. If we consider the X-ray to be light, to be like particles again. So here we have a photon particle, let's say, and we have matter inside the matter there are atoms, and atoms have electrons. So let's say there are these electrons, okay? This photon behaves like a particle. It hits the electron, just like billiard balls hits each other. One is sitting like this, then you poke the other one. It came, it hit, and they both went in different directions. So it happens if, he said, if that's what is happening, but of course you cannot see that. What you see in the end is a detector and you see light. You are not seeing anything happening inside, of course. You just know you sent this X-ray with some wavelength lambda, and then here you have a detector in some angle, right? Some angle phi, let's say, and this detector can move, of course. So you can look at various angles and you see various light coming out, and you see that there is a photon that came out with slightly longer wavelength. And he said, let's imagine that this photon is like a particle. It is hitting this electron, and the electron gets kicked and it moves in this direction with some momentum now, so Pe prime, and it has some energy, Ee prime. Initially, of course, it was at rest, so Pe was 0, Ee was just mc squared. Energy of a body is given by P squared C squared plus m squared C to the power 4. Do you know this? M is the rest mass of the body. Sometimes it's called m0. M squared C to the power 4, and P is the momentum of the body. So when the body is at rest, P is 0, so m squared C to the power 4 only equal to mc squared. So when people say E equal to mc squared equal, that's a wrong equation actually. There is no E equal to mc squared, unfortunately. The complete thing is this, or this can also be written as gamma mc squared. What is gamma? Gamma is 1 over square root of 1 minus beta squared, and beta is just V over C. So 1 minus square root of 1 over V square by C square is gamma. Gamma mc square is also equal to this. So either gamma mc square or this. So what happens is when when V is 0, beta becomes 0, so gamma is just 1, so mc square, okay? So is mc square. Anyway, this is just, and for the photon initially, the energy will be h nu, let's call this E nu, or hc by lambda, okay? And its momentum, the momentum is actually h nu by c. For photon, the rest mass is always 0. So if you put m equal to 0, then E equal to square root of P squared C squared. So E equal to Pc. So P is E over C. So this was for a massive particle. For any massless particle, E equal to just Pc is the relation between energy and momentum. For a massive particle, the relation between energy and momentum is this. So E is h nu, so h nu over c. This is the initial energy and momentum of the photon. This is the energy and momentum of the initial electron. This is still a theory. We don't see these things, okay? We see just this. We are sending our X-ray in, and we are seeing another X-ray coming out. These are the two things we observe. This is all theory. What you do is you send an X-ray and you observe another X-ray coming out in the detector, and based on that, you have some data, you have some tables. Now, can you explain this table using some theory? That's the theory that Compton is proposing, and we're checking this. Now, you can solve this really. If I ask you, find out a relationship between whatever we have. What we really have? We have this lambda, we have that lambda prime, and this angle phi. At the angle you put your detector. So find a relationship between lambda, lambda prime, and phi. What do you have? Two most important laws of nature. Two most important laws of nature that have never been seen violated. What are they? Conservation of energy and conservation of momentum. Here, linear momentum. What is the initial, okay, so what is the initial energy? Energy of the photon, h nu, plus energy of the electron rest mc square equal to finally energy of the final photon, so which is some h nu prime, e nu prime equal to h nu prime, right? Now it's not at rest, it's moving. The electron is now moving. So what happens is, this guy kicks the electron. As a result, this electron takes away some of the energy from this guy and starts moving. That's where it gets its kinetic energy. And this guy loses that energy, and that's why its frequency is now different. P prime square c square plus m square c to the power 4 is the energy, and what is the momentum? We don't know, some p prime. First, use the energy conservation law. Initially, we have the photon, h nu, energy plus the electron, mc square, nothing else. Finally, we have again a different photon plus the energy, call this h nu minus h nu prime plus mc square, and that thing, if we take a square, then we get just this thing, p prime square c square plus m square c to the 4. So we have h nu minus h nu prime whole square, m square c to the power 4, right? And then the 2 h nu minus h nu prime mc square equal to this thing, p prime square c square plus m square to the 4. They're always happy to cancel out things. So just keep, let us keep it like this. P prime square c square equal to this whatever h nu minus h nu prime whole square plus 2 h nu minus h nu prime square. It's important. Again, what will you use for the momentum is momentum conservation. Of course, momentum is a vector, so you have to check its conservation is in two perpendicular directions. Independently, it has to be conserved in this direction and in this direction. So what we have, initially we had no movement in this direction. Electron is at rest and the photon is moving in only this direction. So horizontal direction. Initially, what momentum do we have? We have this p nu plus 0. On the other hand, we now have this picture, electron in this direction and photon in this phi angle, and let's call this theta angle. Okay, so this is p e prime now, and this is p nu prime equal to h nu prime by c. P nu is, I told you, h nu by c. So x direction we are now considering horizontal. What is the total momentum in this direction now? P nu prime cos phi, which is h nu prime by c cos phi, plus p e prime cos theta. That's it. P e prime cos theta equal to h nu by c minus h nu prime by c cos phi. Let's call this 1, this 2. Let's consider now vertical direction. In this direction, initially there was nothing. So 0 equal to, upward we have p h nu prime by c sin phi and sin theta. So that means p e prime sin theta equal to h nu prime by c sin phi, right? Let's call that 3. Here we have a p e cos theta, here we have a p e sin theta. 2 square plus 3 square equal to, we'll just have p e prime square, right? That's it. Then d square u prime cos phi square. We have sin square phi Once again, this thing will add up, right? H square, nu prime square, cos square phi by c square, and here we have h square, nu prime square by c square, sine square phi. So h square, nu prime by c square, plus this thing, of course, h square, nu square by c square, and then what? 2h square by c square, nu prime, cos phi. If I multiply this thing by c square, then we'll have a c square here, c square cancels out, c square cancels out, c square cancels out. So p square c square equal to this, and p square c square equal to this from earlier, energy conservation. We can equate them, so this becomes this. This squared h nu square will be gone, h nu prime square will be gone, cancelled out. Just the cross term will remain, 2h nu, 2h square, nu prime. And from here, this is on the other side. Yeah. This equal to this. So this comes on this side, we have 2h square, nu prime, 1 minus, or cos phi minus 1. This on this side. Okay? Is it clear? Do it yourself at home. It's a simple exercise, really. Equal to this thing, 2h nu minus nu prime mc square. So 1, h will be gone, 2 will be gone, nu prime, let's put it here. So this will become 1 over nu prime. This will become 1 over nu. Take one c inside. What is c over nu? Lambda. Yes. Lambda prime minus lambda. Let's take mc on this side. And you have the final formula in terms of lambda and lambda prime and phi. That's what you asked. Like, this is all we have. We put our detector in some direction, this phi. We have our controlled X-ray that we are sending. We of course know what is the wavelength of that. And we know the wavelength of the X-ray that we are detecting. So lambda, lambda prime, and phi. Okay. So lambda prime minus, I think a sign I got wrong. Yeah, I think it's 1 minus cos phi. So do this calculation again yourself. You know, like just energy conservation and momentum conservation, and simplify. It should be 1 minus cos phi. And it's interesting, now we will see why actually he used X-rays. Let's call this delta lambda, the change in wavelength. So what is the maximum change that can happen really? Looking at this formula. What will be the maximum value of delta lambda? H by mc. Actually, no. When phi is 180 degree. So 2h by mc. So anyway, this h by mc is kind of the measure of how much there will be change, right? So maximum delta lambda will be when this becomes 2. Max, let's say. This becomes 2h by mc. Now, if this could be any particle, okay? If it's a heavier particle, the change will be less because the m is bigger. For electron, if this value is around, I think, 5 picometers, okay? 4.8 something picometers. And for electron, this has a name actually. This h over mc has a unit of length, right? Because lambda has a unit of length. This doesn't have any dimension. So this is a unit of length. And this is kind of the measure of how much the change will be, right? 2h by mc, but at least the same order of h over mc. So it is the measure, the degree of how much change there will be in a wavelength if you send some light. So this is called actually Compton's wavelength, lambda c. It's called Compton wavelength. So you can also write lambda equal to lambda c, 1 minus cos phi. Quantum wavelength is different for different particles. It's less for heavier particles. For electron, it's 2 point something picometers. So for an electron, maximum change will be the light goes this way and gets reflected back towards you. Right? That's when U phi will be 180 degree. So you have the target and you send some X-ray, it bounces back in this direction. That will lead to the maximum change because your phi will be now 180 degree. Yeah, right? And that is like 5 picometers. How much fractional change is there? So how will you measure this? You had some lambda wavelength and the change is del lambda. So what is the fraction of change? Del lambda by the lambda that you send, right? Times 100 will give you percentage change. So if you do this calculation, I'll actually tell you to do this. Do it for visible light. So you know what is the lambda for visible light. It will be somewhere around 380 nanometers to 700 nanometer. Take something in the middle, 500 to be easy, 500 nanometers. And check out what is this. So it will be 5 picometers divided by 500 nanometers. You will see that this is maybe 0.01 or 0.001%. So the change is insignificant. Okay, but if you did this for X-ray, take X-ray, 0.1 nanometers to 10 nanometers. Let's take something in the middle, 5 nanometers, and calculate this. You'll see it's around 10% or something. So significant change. Okay, so the X-ray loses more energy actually during this kind of interaction with matter than compared to visible light. In fact, light loses energy in various ways. Okay, various waves you will find in later in this course or in other courses. Turns out for X-rays, this is the chief mode that X-ray loses energy through Compton scattering. So when light is passing through a plastic, it hits electrons of the atoms and loses 10%, 10%, 10%, a huge amount of energy like this. So this is a small problem that you will do. Just show that this is significant change in its wavelength when you use X-ray compared to visible light. Okay. How much time? Kiman time ase amar? First minute. Okay, it's not bad. We can at least introduce another topic. He is French. He's French, so I'll try to pronounce his name in French. Because people hate when you tell you Dipazuti or something. You will probably hate it, right? So at least let's try. French is very tough. It's like the voy, actually. It's something like the voy. But people call it de Broglie or de Broye, some people. But R is like in French. Louis de Voy. Go find its pronunciation on YouTube and practice. I mean, we should always try to pronounce people's names correctly. It was his thesis, I think 1924, PhD thesis. He was a student of history, actually. His brother was in physics, and he followed his brother. He was inspired by Bohr's atomic model. There are some fixed orbits. So it's this orbit or this orbit. Electron cannot exist somewhere in the middle. That's Bohr's theory, right? It's something like a standing wave. For example, if you had a string tied, we come back to this example again and again. There can be this wave, or there can be this wave, or like this. At least the end point must be this. So if you brought it back and tied in one point, so it becomes a circle. So it's either this wave or like this wave or like this. So they perfectly match. So the orbits where they perfectly match, those were allowed. So that maybe every particle had some sort of waves associated with them. Another inspiration was So light, of course, light, we had seen that it's wave, it's behaving like particle. So what is it? E equal to PC. P is hc by lambda. So Cc goes on P equal to h over lambda. This is for light, we know this. He said, let even other particles with mass are probably like this. They also have an associated wave. What is that wave? Let's come to that later. But they have an associated wave with them. So if we really did that, then we assert, he said, this equation is valid for everything, not just light, everything. If something had a momentum, it's moving, then it has a wave associated with it, and the wavelength is given by lambda. So for light, of course, P is just P. I mean, there cannot be a mass time velocity. There is no rest mass. Okay, so it's just P. But if you had a massive particle, then what is P? Is non-relativistically mv, but in relativity there will be a gamma. Gamma is again 1 over square root of 1 minus v square by c square. So this. So for a massive particle, you could just write this. Of course, momentum is there, but if you wanted to write it in terms of mass and velocity, then that's lambda equal to h over p, which is gamma mv. So he said for any particle that is moving has a wave associated with it. Now, I leave it to you. Just use a tennis ball. Okay, this tennis ball with some mass, 50 grams, and it's moving with a velocity, let's say 30 meter per second. And see what is the wavelength that you come up with. Tennis ball also have an wave associated with it according to the boy. You people should also have, if I'm moving, then I must have a wave associated. What is that wavelength? Just calculate for the tennis ball. You will see that the wavelength is so small that it's smaller than the size of the tennis ball. Now, if the wavelength is smaller than the size of the tennis ball, then it doesn't matter. We can perfectly consider the ball to be a particle. Forget about the waves. So just do that exercise. And I'll elaborate in the next class. But in this class, I'll just tell you what this wave is. Just to introduce it. So wave, what is water wave? Like this. When it's steady, when the water is steady, its height will be more or less like this. Right? There is a pool, swimming pool or a pond, water will be like this. If you created a wave, then sometimes it will go below its initial level, sometimes up. So it's the wave of the height or depth. That's the wave. It's the height of water that's changing with time and space. What is sound wave? It's the wave of pressure. Air gets compressed or expanded in some point, like this. That's pressure wave. Sound is pressure wave. Light is electromagnetic wave. Each point electric field is increasing, magnetic field is decreasing, electric field is increasing, magnetic field. So in perpendicular direction, electric and magnetic field are just changing their strength. That's our electromagnetic wave. What is the Boy wave? What is this wave? It has to be a wave of something, right? So I know, okay, a body is moving, and with it, there is an associated wave due to the void. What is that wave of?